Next, what I want to do is talk about a few caveats here. So I want to know, are the vectors 0 and v linearly independent? I haven't even told you what v is. V can be whatever vector you want from whatever vector space you want, and the answer is going to be no, they're not linearly independent. And that's because you can find a solution where, so the answer here is no. And the reason why is that one is a multiple of the other, right? 0 is essentially 0 times the vector v. So that means that one is a multiple of the other, and therefore they're not linearly independent. To find another solution, so equivalently, we could write something like 4 times the 0 vector plus 0 times the vector v is equal to the 0 vector. And here we have a constant c1 and c2 that are not both 0. It's okay that one of them's 0, but they're not both 0, so that their linear combination, that sum, is equal to the 0 vector. So it turns out that whenever you include 0 in the mix, you automatically lose linear independence. So it doesn't matter what the vector is, what the vector space is, the 0 vector and v, whatever vector v is, are always going to be linearly independent. Okay. One other thing to know is that for certain vector spaces, such as R2, R3, the set of polynomials of degree at most n, the set of matrices. So for all the kind of basic vector spaces that we've talked about, it turns out that there's a magic number of vectors. And so what I mean by that is that in R2, any 3 vectors are linearly dependent. Doesn't matter what the vectors are, any 3 vectors are linearly dependent. So if I ever ask you, are these 3 vectors in R2 linearly independent or not? The answer is that they're always linearly dependent. Doesn't matter what the vectors are. Any 3 vectors in R2 will be linearly dependent. That makes sense geometrically if we think about what it means to be linearly independent. It means that one of the vectors cannot be written as a multiple of the other. So this is impossible in R2, and let's just draw a picture to think about this for a second. So the picture I want to draw is, let's say we have 2 vectors. So here's a vector, let's call it u. And if I want there to be a chance that 2 vectors are linearly independent, they can't lie along the same line through the origin. So in other words, if I pick a vector that's some scalar multiple of u, then automatically we lose. They're not linearly independent anymore. So in order to get linear independence, I must pick something else. I must pick some vector that's not on that line through the origin. Okay, so this maybe is v. But there's a problem with that. And the problem is that we've already seen that in R2, 2 vectors that do not lie along the same line are going to span R2. In other words, every vector in the plane can be written as a linear combination, so it doesn't matter what the vector is. Every other vector can be written as a linear combination of u and v. And therefore, the 3 vectors are going to be linearly dependent. It does not matter what this vector is. Okay, so that's the argument. Any 3 vectors in R2 are linearly dependent. Likewise, you could make the same argument in R3. In here, any 4 vectors are linearly dependent. Same argument, you just have to argue geometrically in 3 dimensions. This is also going to be the case in P2. So in P2, again, any 4 vectors. In fact, this is the same statement as above, so let me just copy it while I say it. Any 4 vectors in P2 are going to be linearly dependent. Doesn't matter what they are. And then finally, M22. If I look at the set of 2 by 2 matrices, Here, the magic number is going to be 5. Any 5 vectors are linearly dependent. Okay. So this tells us something actually pretty deep about these vector spaces. There's a proper number of vectors when we're worried about linear independence. That if we want any vectors to be linearly independent in R2, we must have at most 2 vectors. Likewise in R3 and in P2, if we want a set of vectors to be linearly independent, we can have at most 3 vectors, because 4 or more ruins linear independence. Likewise, in the set of 2 by 2 matrices, any 5 vectors are going to be linearly dependent. So if we want a set of vectors in the set of 2 by 2 matrices, if we want those to be linearly independent, we need at most 4 vectors. Again, now I'm back to using vectors just to mean as elements of a vector space like we're talking about. Okay, so these ideas will be relevant for us in the next section.